everybody. Hope all is going well. In celebration of me finishing or passing Calculus 3, I want to go over this problem specifically. This problem was definitely one of the harder problems on my exam, and it showed up on almost any exam that I did as practice. So we'll start off with part A. So for part A, it's the surface integral. Is the surface integral, so we have the double integral of h of x squared y squared plus z squared ds, positive, negative, or 0. For this, you don't really have to do much work for it just because inside of the integrand, if whatever we put in there, it will always be a positive due to the squareds. So we know it's going to be positive. Okay. Now B. The vector field f, which is equal to y plus z, comma, negative x, comma, yz, has the curl f, or we'll call it curl f, equal to z1, 2, negative 2. There you go. The flux, so we have the flux, the double integral, s of the curl f dot n ds is, so now we're using the surface S, so we're going to be using this surface here. Okay, so with a surface integral, or with, this is Stokes' theorem, so with Stokes' theorem, we can see that if we take this right here, it's going to tell us everything about the inside of this. So with a curl, let's see, this can also be equal to the same integral f dot dr, but why would we want to do that? Let's see. You know, if we can parameterize it. So we can parameterize it, I guess, as a circle given this position here. Yeah. So let's see. R is equal to R. Does it tell us the boundary of S is a unit circle, so it's going to be cos t sine t 0, because we don't have anything in the z-axis, it's all going in the y and x direction, okay? Other than that, well, I guess since it's going counterclockwise, we can change these up. There you go, so switch those around. Now, we have dr, which is going to be, and yes, I was correct, so since we're getting Stokes' theorem here, we can revert this back to its original, which is going to be f dr. Our dr is going to be cos t negative sine t 0, and basically dt. And now we just set up our integral, which is going to be from 0 to 2 pi of f, which is this here, and we'll just make it into terms of t, which is going to be, we sub in our y, which is cosine, so it's going to be cos t plus 0, comma, negative x, which is negative sine t, comma, cosine times 0, which is 0, dotted with, let's not forget that it's dot, dr, which is cos t, negative sine t, 0, dt. So now with this, we can go ahead and do our dot product, which ends up giving us integral from 0 to 2 pi of cosine squared t plus sine squared t plus 0 dt. So now we know that this here is 1. So now all we have is a simple integral, 2 pi. So that's our part B. Okay, so that was part B. So for part C, we're asked for G equals XYZ, is the flux positive, negative, or 0? So we're using our same surface again, which is pretty good, I guess. And now we're going to do the divergence theorem for this one. So if you recall, the divergence theorem turns our flux into a triple integral of some surface or some region area, and maybe do the divergence of that dv. So now the thing is, we have an issue here now. We can't just do this theorem like this. There's actually one thing we're missing. Now, for this surface here, it's not closed off, so unfortunately. So it's kind of like I don't know, like those Viking horns. I don't know if you know what I mean, but this area here, we actually have to close it off. So we're going to make it another surface. We're going to go ahead and call this S1. So what I do is plus the flux of S1 of G dot N ds now is equal to the triple integral, horrible integral signs, of E of del dot g dv. Now E, we're going to say E is the region, so we're going to say the region inside S and S1. Okay. So what we want to find though is this. So what I'm going to do is I'm going to start by finding the divergence real fast. So we'll do that right here. If you recall, divergence is equal to partial x, partial y, partial z dot our vector field. So which is g, which we were told is x comma y comma z, which comes out to 3. Now the reason for that is since we're dotting it, we're going to add them together once they're done. So this and this is going to become 1, this and this is going to become 1, and this is going to become 1. So that's 3. We can go ahead and substitute that into our integral. So we're going to say probably not going to be rewriting this whole thing each time, but we get the gist of it. So that's going to be E3D. Boom. Now let's go ahead and solve this here. All right. So now for that, sorry, it's S1. So now for that, let's go ahead and do this. So we're going to say that integral S1 G dot NDS. It's going to be the unit disk. So we go ahead and parameterize that and say R of X of Y equal to X, Y, 0. C Rx is equal to 1, 0, 0. Ry 0, 1, 0. Remember that this can be substituted with the magnitude of Rx cross Ry, which just ends up coming out to be 0, 0, 1, which makes perfect sense, to be honest. Now, we want this in terms of G. Well, let's put this equal to, we have G of R X, Y. It's going to be equal to X, Y, 0. Go ahead and write that down. G of Rx. Now, I guess we're basically just doing the dot product now, so we could just go ahead and substitute that in here. So that right here, G dot, so we have X, Y, 0 dotted with 0, 0, 1. This whole thing just equals to 0. So since that's equal to 0, we now know that the integral for S of G dot NDS is equal to our triple integral of 3 dV. So now since we have 0 here, we basically have a positive now. So now that tells us that this is going to be positive. All right, guys. So now for part D, basically the same idea, except now we have E as our vector field. For part D, yeah, we have E as our vector field, and now we have to actually solve for it. So we're going to take the same idea of S1, the region E, which we will now be calling R because we just happen to be E here. And yeah, so let's go ahead and find our divergence of E. Just del dot E, which actually ends up being 0, surprisingly. Substitute that into here, this whole thing just goes to 0. So we're left with flux over surface S of E. Plus the double integral of S1 of E dot NDS. Let's be a little clean here. Equals 0. We'll go ahead and find this here. It's gonna be pretty similar to our last one. So we could say like our double integral of S1 of E dot NDS. We're going to do the parameterization again. We have R of XY is equal to X comma Y comma 0. Got our R of X is equal to, let's see, 1, 0, 0. R of Y is equal to 0, 1, 0. Cross both of these to get our normal. Okay. So now this is equal to the double integral of S1 of E dot, wait, actually, yeah, okay, hold on. E dot our normal, which is 0, 0, 1. I don't know, I guess we'll keep it as DS. Actually, it'll be DA now, the area. now equal to S1 of E. We'll plug in E into here. ZX2 gives us 2. Actually, be 2 times the area of E, which is the unit, which is the circle here, which the area of a unit circle is pi. It's equal to 2 pi. Now we have that this here plus 2 pi equals 0. We solve for that and we get that this is equal to negative 2 pi. Yep. There's that problem. It's certain, if you go to a certain institution, it's certain that this will definitely be on your exam, your final exam, almost every time. It's been around every practice problem I've done. Every practice exam I've done, sorry. But yeah, here's my video on that. Good luck to everyone taking Calc 3 next semester. Yeah, have a great one, guys.